Good day, everyone. My name is Mario Baginas, and I'm currently a third semester geophysics student at the University of Oklahoma, working under Dr. Heather Beadle. Today, we'll be presenting the work that I'm doing with the ASPE program, which is a supervised machine learning approach to discriminate gas saturations in the Gulf of Mexico using frequency and spectral shape attributes. So really quickly, we're going to just go over the outline, which is going to be the motivation, which is what is the problem with low gas saturations and what has been done to solve this problem, what has not been tried, and the current differences we know from the varying amounts of saturations, and the solution that I propose. We're going to go over the geologic setting, as well as the methods, and some preliminary results, which is going to include the histogram and crossplot of the attributes selected per label, as well as the SHAP values that are extracted from the training, and the random forest preliminary results. So first off, we know that in the hydrocarbon exploration stage, there are many uncertainties stemming from the seismic data. Companies tend to drill bright spots because they serve as an indication for hydrocarbons, yet this doesn't always lead to successful results when dealing with gas. The bright spots are caused by the gas reducing the seismic wave velocity, and low amounts of gas saturation, 1 to 50%, tend to produce nearly identical bright spots compared to high amounts of gas saturation. This is due to the just small amount of gas saturation drastically reducing the bulk modulus and producing said bright spot. So what has been tried before? Currently, the industry approach is to solving this problem is the amplitude versus offset method. The higher saturation of gas produces higher amplitude response at higher offset angles. This method, though, requires pre-stacked seismic data, and it is not successful every time since dry holes have continued to be drilled using this method. Theoretical models have been created to try and differentiate the different gas saturations. We know that frequency discomposition of pre-stacked data do exhibit different responses with different amounts of saturation. Lower frequencies are affected more by this variation in saturation, and the attenuation of the seismic wave is higher in low gas saturations. Attenuation can be estimated from spectral shape attributes, which are skewness, kurtosis, roughness, and slope. Other approaches that have been tried that are relevant to our research is that supervised and unsupervised machine learning algorithms with the right set of attributes can distinguish geological phases, and a unsupervised machine learning approach was used to distinguish gas saturation successfully using principal component analysis. What has not been tried is testing the theoretical models previously mentioned in field seismic data, as well as creating a supervised machine learning method that can produce gas in a different field. What other differences do we know from the differences in saturation? We know that low frequency shadows can be observed below reservoirs of high gas saturation, as well as we also know that the spectral bandwidth of high gas saturations is wider than those in low gas saturations. So what I propose is a supervised learning algorithm that uses a set of frequency attributes to discriminate between low gas saturation reservoirs, high gas saturation reservoirs, oil, water, and node reservoirs using only post-stack seismic data. The attributes that will be used are skewness, kurtosis, roughness, and slope. These are the waveform analysis attributes that are considered for attenuation, the spectral bandwidth, as well as the average frequency, peak frequency, and spectral decomposition components at 2 Hz intervals. We will be using CMP spectral decomposition for its ability to really discriminate within reservoirs. On the right, we have the covariance of all the attributes, and as you can see, they all have different covariances between each other, and the most similar ones tend to be the frequency discomposition attributes that when you compare them from a very low frequency to a very high frequency, they tend to be very dissimilar. The result of my research is going to help create an analysis of these attributes to better understand the differences that are created depending on the varying amount of saturation. The area that we're going to be testing, training and testing will be the Ursa field. This is going to be characterized by a vertical well that contains both high gas saturation, low gas saturation, and oil. And we're going to be then testing on the King Kong and Lisa Ann field located further west, which contains low gas saturation a high gas saturation, an oil well, as well as a dry hole. So the testing area we're going to be using is the Ursa field. This is characterized by stacked pace, and all the reservoirs are of equal porosity. And we can see that the first reservoir is low gas saturation, followed by 19 feet oil and a 55 feet oil further below. Then we have a high gas saturation, followed by two more oil reservoirs at the bottom. The testing area is going to be the King Kong and Leeson Field, where we're going to have a variety of different wells with different amplitudes perceived and different fluids found in them. Well A, which is the Lisa Anfield, is located further east, and this is characterized as being a low gas saturation well. As we move west in our random line, we see that we have well B, which was an oil reservoir, and as we continue further northwest, we have the King Kong field, which was characterized by three wells that were mostly gas with some oil. And if we go further down dip from King Kong, we actually had a low gas, a dry hole in this area, which exhibits the same amount, if not higher amplitude, than all the other wells around the area. For our workflow, we're going to start with the well data, the Ursa seismic amplitude, and the King Kong and Lisa Ann seismic amplitude volumes. Both the Ursa and King Kong are going to be cropped to the pertaining size for our investigation. From then on, we're going to use our well data and log interpretations to make horizon interpretations in both of them to further know where our reservoirs were. From then, we continue only on the Ursa field, where we're going to be using that as our training. And for our horizon interpretations in the stack reservoirs, we're going to create labels of low gas, high gas, oil, water, and non-reservoir. We're going to create our attributes in both our volumes, and then we're going to create create a scaling from 0 to 1 from both volumes so they can be correctly characterized for the machine learning algorithm. For my research, we're going to be testing k-nearest neighbors, decision tree, and random forest supervised learning algorithms. But for the purpose of this presentation, we're just going to cover random forest, and we're going to be going over the hyperparameter optimization, grid search cross-validation, model building, which produces a confusion matrix, along with then we have the blind test there. We decide this is our winning algorithm. And with that, we're going to use it to test it in the King Kong and Lisa Ann field. For our labeling, this is kind of the most important part in our research, is the first step. And what you can see here is the stack pay. The training area is going to be just centered in between this yellow dash box. We're avoiding the west side because that's a salt dome present in there, and we don't want the high amplitudes that could be more pertaining to the salt dome contact to affect our training. As you can see on the right, we can actually see the aerial extent of our training. It's going to be 10 to 15 inline crosslines, 10 inlines, 15 crosslines, center mostly around our well. And the way we did this, we created a Hilbert 90-degree phase rotated Hilbert transform in our data, and we were able to map from zero crossing to zero crossing in all our reservoirs. And you can see the labels that we have attached to them. Then we created a layer cake volume where each reservoir or each zone had its own amplitude volume, which we used to then be able to extract each reservoir at different intervals to be used for our training. With the extraction of all the horizons in our original amplitude, we can actually then run all the other attributes that were mentioned in the beginning. And what we can see here is a histogram of each of those training labels and how they compare. At the very top, we have the four spectral attributes. We see skewness and kurtosis don't have much differences between them, but we do see that roughness and slope produces different responses depending on the type of fluid and its saturation. Along with that, I wanted to show you guys a couple of other attributes. Here we have bandwidth, mean frequency, the 4 Hz and 12 Hz and 42 Hz transposition. What we can see here is that the 42 Hz, all of the labels in our reservoir seem nearly identical. But as we go from 12 to 4, we actually see that there's a distinction between each label and the actual frequency associated to them. And this is also visible in the mean frequency. as well in the bandwidth. What's interesting to note here is that oil has the lowest bandwidth. I attribute this to possibly having areas where we have just really high, strong amplitudes from the oil reservoir, and that will produce just a small bandwidth of high magnitude frequencies, while the low gas saturation might be characterized by a low bandwidth, but a mostly low frequencies. And we're going to see how that can affect the result. Here we have a crossplot of the attributes we mentioned before. You can see here the 4 Hz by 50 Hz, and you can see that we can actually have two oil, low gas, and high gas can be very different, but oil it tends to have a higher 50 Hz frequency compared to all others. If we look at a crossplot between 4 Hz and 12 Hz, we can actually see a separation between the low gas reservoir and the oil. In bandwidth, we actually see that high bandwidth is associated to most of the non-reservoirs, and this is compared to the 18 Hz, and you can actually see that there's a difference between bandwidth and low gas saturation. Here we have slope and skewedness, and here we have roughness and kurtosis, and we can see that we do have different distinctions happening between them. So this is all an initial test that we need to make sure that our attributes and labels actually show distinct differences between our attributes in order to expect results that are correct with the science. As we move on, we actually see the results that were produced from this training using random forest. Here's a map view of the previously shown amplitudes that we had for the King Kong and Lisa Ann field. We do see a lot of oil being present here. This is something that I'm currently trying to work on to reduce. But what we can see if we zoom into this area over here in the King Kong field, and we see the cross section, here's the well path and the well label, basically indicating that this was a dry hole and this was a high saturation well. And we can see here that at the top of the dip, we do have a cluster of red, and at the bottom, we do have a cluster of purples. This is indicated as a high gas saturation and this low gas saturation. This is really good results, considering that this is a different data set from where the training was performed. We can also see that we have this aura of oil being present, and we're going to explain why this might be happening later on. We do see that we have another bottom reservoir here, which is where most of the oil was present, but we have a lot of oil being overrepresented, right? If we go further down to what we call well B, we have a lot of oil being present here, and we can see a very consistent oil horizon happening between the top and bottom of our reservoir. And as this was actually an oil well as represented by the green well path. And if we move further east towards our well A, this was our Lisa Ann field, which was a low gas saturation well as represented by the purple well path. We see that right now we're having a misclassification of oil. This is something that I'm currently working on to try and minimize. I have some ideas on why that's maybe happening. What's interesting to note is that it's not as well drawn out as the previous oil reservoir. There's a couple of voxels present there that seem to be classified as non-reservoir, which is more expected. In this slide, I'm showing a random line going through all of our wells, A, B, C, and D. This will be Lisa Ann, and this will be King Kong. Here's where we can see that we have not, if we start with well B, we can actually see that it's a very consistent oil horizon through and through. While when we look at the low gas saturation Lisa Ann, we see that it's not as well labeled as the other one. This is something I'm trying to work on. This should be represented as non-reservoir purple. And here we can also see the effect of the green aura happening above our reservoir of interest being labeled as green. I wanted to show that the reason this is happening is due to the frequency discomposition. It causes a vertical smear in the amplitudes which decrease, and this is causing the misrepresentation of the oil voxels above our reservoir. This is something that we need to keep in mind moving forward, and we should keep our observations just at the top and bottom of our reservoir and not extend them past it. Underneath King Kong and Lisa Ann, we do see that the results here are from a different response and are not being confused with the one above. This is one of the reasons that we chose CMP discomposition for a way lower vertical smear than would be present in CWT discomposition. Here's a little example of the bandwidth attribute and how it compared to our model results. We are in the King Kong area where we had the high gas saturation and the dry hole. And we can actually see that in this case, it's a little bit different from our expected training, where we actually seen higher bandwidth in the low gas saturation and lower bandwidth in the high gas saturation. But if we do go to the next slide, we can see here in the Lisa Ann field where we have our overrepresentation of oil. We actually have the lowest bandwidth visible here, which would be expected of a low gas saturation reservoir. This is what I tried explaining at the beginning, that our oil reservoirs seem to be training to be an even lower bandwidth than the low gas saturation. And I attribute this to the idea that oil reservoirs tend to be low bandwidth but of a high magnitude of frequency, while the low gas saturation reservoir would be low bandwidth of low frequencies, of magnitude frequencies. So this is something that I want to work on in the future, seeing how we can reduce this and have a better representation of bandwidth when it comes to low bandwidth because of low frequencies or low bandwidth because of high frequencies. Moving on, we're going to be looking at the SHAP values. We're going to show the attribute importance and how they were used for the training. Here we actually have a list in order of how strong each attribute was being represented and used in order to create the training and the results. And we can see that we have a preference for the 10 Hertz and 8 Hertz, 12 and 12 Hertz. So we start with the low frequencies, then move on to the higher frequencies, then peak frequency. And if we go all the way down, we can actually see that skewness, bandwidth, and kurtosis seem to not be of much importance when deciding the final prediction in our model. We can do SHAP is be able to separate each of the labels and understand how all of them are affected in the training. So here we can actually see that low gas is used in the 10 Hertz and 12 Hertz, 14 Hertz to more accurately predict its prediction. But if we look at the high gas attributes, the list is actually represented by higher frequencies. If we go into oil, we see that we actually have a very similar response to the low gas with a different list of attributes present. To finish off, I would like to point out that what's left for my future work is to kind of fine-tune the hyperparameters of the model to have better results. We do know that we have wrong results happening in the Lisa Ann area where we were over predicting for oil when it was low gas saturation. This is an example of a model that it's working a little bit better. We're having a little bit less presence of oil, and we having non-reservoir being represented here in Lisa Ann, and this is kind of what I'm working towards to be more consistent. And in the future, I'm trying to extend my search area to this extent, where you can see we have some bright amplitudes over here, and what you can see here is the same red boxes being shown in both. And we're going to be including a dry hole, a couple of oil wells, a couple of gas wells, and another section of oil wells. So this should be really good to compare and really test the robustness of our algorithm. And with that, I would like to thank everyone for watching this presentation. I'm still working hard to make it all kind of fall into place and get this kind of published. So thank you for being here, and thank you for supporting the ASPE program. I hope you have a great day. Thank you.